For millions of rural Indian farmers, agricultural extension work breaks down at two critical points. Accurate government lab testing takes too long to influence the current crop cycle, and digital data portals require unfeasible levels of technical literacy. Pushing complex web apps or relying entirely on personal smartphones fails to account for a demographic burdened by minimal digital literacy, inconsistent network coverage, and limited local device storage. The AI Krushimitra booth bypasses these bottlenecks entirely. It is an integrated, stationary hardware-software ecosystem designed specifically for zero-friction use at the village level. To understand how it bridges the access gap, we have to reverse engineer its three primary layers: the physical edge sensors, the vernacular user interface, and the low-bandwidth expert routing network. Building effective agricultural technology for this environment requires a full-stack, first-principles systems engineering approach. The physical sensing constraint is time. Standard government soil laboratories provide high accuracy, but their multi-week turnaround times render the data practically useless for immediate field interventions. The hardware solution localizes the processing power using a low-cost ESP32 microcontroller, effectively turning the physical kiosk into an edge computing hub. This hub connects directly to a 3-in-1 sensor probe, built to measure soil moisture, temperature, and electrical conductivity, or EC. But the development logs from July 12th document a significant engineering roadblock. When tested in loose soil, the EC readings fluctuated wildly, returning highly unstable data. To stabilize the output, engineers executed a strict calibration pivot, resetting the microcontroller's baseline to account for the varying densities of local field soils. This chart compares the sensor's output against official laboratory results. We see a close alignment across moisture, temperature, and EC levels. While there are minor deviations, such as a 0.2 difference in electrical conductivity, these margins are statistically acceptable for immediate field triage. Instead of waiting weeks for perfect precision, a farmer receives actionable data instantly, allowing them to adjust fertilizer application or irrigation on the exact same day. Optimized edge IoT sensors trade microscopic lab precision for macro-level speed, providing significantly more utility during active crop management. Moving up to the human-computer interface, standard security protocols present another immediate barrier. Traditional alphanumeric passwords often prevent rural demographics from accessing digital services. The architecture solves this through a biometric pivot. A simple fingerprint scan links to a user's Aadhaar or mobile number, granting instant, keyless access. Once logged in, the dashboard enforces a strict visual hierarchy. It replaces dense text blocks with a grid of large, recognized icons representing agricultural services. The localized Marathi text beneath each icon acts strictly as a secondary fallback for semi-literate users, keeping navigation entirely visual. For complex queries, the system integrates natural language processing to power a voice assistant capable of understanding regional vernacular. According to field trial metrics, this NLP integration achieved an 87% accuracy rate in successfully parsing spoken commands. This multimodal approach allows the kiosk to deliver highly specific data, like precise ingredient ratios and preparation methods for organic pesticides. Without the icon-first visual design and voice assistant to guide the interaction, this dense, actionable information would remain completely inaccessible. Effective agricultural software must completely abstract its complexity. It has to remove all cognitive load related to navigation and input, allowing the user to focus solely on the agronomy. The final layer addresses a severe networking constraint: how to physically route high-level agronomic expertise, like PhD-level scientists, directly to geographically isolated villages. Initial attempts to bridge this gap failed financially. As documented in the July 18th engineering logs, licensing enterprise video APIs from companies like Zoom drastically inflated the project's software overhead. The team executed a critical technical workaround on July 21, sourcing a free third-party API from Zixasoft to handle the back-end communication routing. The interface presents users with a direct directory of available specialists, displaying their specific disciplines, from plant pathology to entomology, along with real-time online availability. When a user selects an expert, the system automatically aggregates the kiosk's recent edge sensor readings into a single consolidated data packet. Rather than forcing the expert to download a proprietary receiving application, this packet is pushed directly to their personal WhatsApp account. This asynchronous text and link-based communication requires minimal data, providing a highly reliable connection in areas heavily constrained by limited 4G bandwidth. Leveraging ubiquitous pre-existing networks like WhatsApp scales the reach of these experts instantly without compounding the hardware's ongoing server costs. To deploy this full-stack architecture at a village panchayat level, the system requires a highly compressed economic footprint. The iterative MVP prototype was constructed for a total hard cost of exactly 43,300 rupees. Even the projected production model, estimated at under 14 lakh rupees, represents a fraction of the capital required to build, equip, and staff centralized government laboratories. The system's viability relies entirely on its three structural pillars working in tandem: ESP32 edge sensing for rapid field data, a multimodal biometric and NLP user interface, and low-bandwidth WhatsApp API routing. The AI Krushimitra proves that successful technological deployment in emerging markets relies on engineering advanced systems that seamlessly fit the user's natural environment.